Welcome to the world of context engineering. Think of it as the next big step after prompt engineering. While prompt engineering is about writing good instructions for large language models, context engineering is a much broader field. It's the formal discipline of designing, managing, and optimizing all the information, the entire informational payload that an LLM needs to perform complex tasks. The performance of an LLM is completely dependent on the context it's given. This context can be anything from a simple command to a massive external knowledge base. As LLMs have grown from just following instructions to becoming the reasoning engines for intelligent agents and complex systems, the way we manage their context has had to evolve too. This survey organizes the field into two main areas. 1. Foundational components. These are the basic building blocks of context engineering. They include context retrieval and generation, how we get the information, either by crafting smart prompts or pulling from external knowledge sources. Context processing, how we handle that information, especially when dealing with very long texts, refining it for accuracy, or integrating different data types. Context management, how we organize the information, using techniques like memory systems and data compression to stay within the model's limits. 2. System implementations. This is where the foundational components are put together to build sophisticated AI systems. These include retrieval-augmented generation, systems that dynamically pull in external knowledge to provide more accurate and up-to-date answers. Memory systems, giving LLMs a form of memory to recall past interactions much like humans do. Tool-integrated reasoning, allowing LLMs to use external tools like calculators, search engines, or other APIs to interact with the world and perform complex tasks. Multi-agent systems, creating teams of AI agents that can communicate and coordinate to solve problems that a single agent couldn't handle alone. A key finding from analyzing over 1,400 research papers is a major research gap. There's an asymmetry in what LLMs can do. They are becoming incredibly good at understanding very complex and long context, but they still struggle to generate equally complex and long-form outputs. Closing this gap is a top priority for the future of AI. This survey aims to provide a unified map for both researchers and engineers to navigate and advance this exciting field. Chapter 2. Related work. Before diving deep into context engineering, it's helpful to see how it fits into the broader landscape of AI research. A lot of previous work has surveyed specific parts of what we now call context engineering, but they've often been studied in isolation. This survey is different because it provides a unifying taxonomy that connects all these different areas, showing how they are all part of a larger, more systematic approach to managing an LLM's information flow. Here's a quick look at the existing research. On foundational components. There are many surveys on prompt engineering, which catalogs different ways to write instructions for LLMs. Research on external knowledge retrieval often focuses on how to connect LLMs to knowledge graphs and other structured data to make their answers more factual. Long context processing is a hot topic, with many papers analyzing how to optimize the attention mechanism in transformers to handle longer and longer texts without slowing down to a crawl. Context management, which deals with memory and compression, has been explored, but often as part of other topics rather than as a unified field. On system implementations. Retrieval-augmented generation, RAG, has been extensively studied as a way to reduce hallucinations, i.e., making things up, in LLMs. More recent work has looked at advanced, modular, and agentic RAG systems. LLM-based agents are a huge area of research, with surveys covering everything from how they are built to how they plan and make decisions. Tool-integrated reasoning has been well documented, showing the evolution from simple systems that use one tool to complex frameworks that can orchestrate many. Multi-agent systems, MAS, are another major focus, with research detailing how multiple AI agents can communicate and coordinate to achieve complex goals.
Finally, evaluation is a critical area, with many papers analyzing the benchmarks and methods used to test all these different systems. While all this previous work is valuable, it creates a fragmented picture. The connections between, for example, using RAG as a form of external memory and using prompt engineering to control that memory are often not made explicit. This survey's main contribution is to propose context engineering as a unifying framework that brings all these disparate fields together under one roof, providing a holistic map of how context is generated, processed, managed, and used to build the next generation of AI.
Chapter 3: Why Context Engineering. As AI systems become more complex, simply engineering a prompt is no longer enough. We need a more systematic and scientific approach. This is where context engineering comes in. 3.1 Definition of Context Engineering. At its heart, an LLM is a probabilistic model that tries to predict the next word in a sequence, given some initial context. In the old days of prompt engineering, this context was just a single, static piece of text. Context engineering redefines this. Instead of a single prompt, the context C is a dynamically assembled structure of different informational components. Think of it like a recipe where you combine various ingredients. C equals assemble C1, C2, Cn. These components or ingredients include C-inster, the system instructions or rules. C-know, external knowledge retrieved from a database or knowledge graph. C-tools, definitions of available tools the model can use. C-mem, information from past interactions, the model's memory. C-state, the current state of the user, the world, or a multi-agent system. C-query, the user's actual immediate request. From this perspective, context engineering is a formal optimization problem. The goal is to find the perfect set of functions for retrieving, selecting, and assembling these components that produces the best possible output from the LLM, all while staying within the model's context length limit. This shifts the focus from the art of prompt design to the science of information logistics. 3.2 Why is this so important? 1. Current limitations of LLMs. LLMs have some serious technical hurdles. The self-attention mechanism, which is what makes transformers so powerful, has a computational cost that grows quadratically with the length of the text. This makes processing very long contexts incredibly slow and expensive. LLMs are prone to hallucination, making things up, are sensitive to small changes in input, and can produce answers that sound plausible but are semantically nonsense. 2. Performance enhancement. Good context engineering dramatically improves performance. Techniques like RAG and structured prompting, like chain of thought, help LLMs reason through complex problems step by step, leading to huge gains in accuracy. For example, chain of thought prompting has been shown to improve accuracy on arithmetic tasks from 17.7% to 78.7%. Providing a few examples, few-shot learning within the context can lead to significant performance boosts in specialized tasks like code summarization or bug fixing. 3. Resource optimization. It's more efficient than constantly retraining models. Instead of expensive fine-tuning, you can intelligently filter and provide the right information directly in the prompt. This optimizes the use of the context window and reduces token consumption, which saves both time and money. 4. Future potential. It opens the door to more advanced AI. In-context learning allows models to adapt to new tasks on the fly without needing to be retrained. Advanced reasoning techniques like chain of thought and tree of thought lay the foundation for more nuanced, context-aware AI applications that can handle complex, real-world problems. Chapter 4: Foundational Components. Context engineering is built on 3 core pillars that manage the flow of information for an LLM. These foundational components are the essential building blocks for creating any advanced, context-aware AI system. 4.1 context retrieval and generation. This is the first step, getting the right information to the LLM. It involves 3 key mechanisms. 1. Prompt engineering and context generation. This is the art and science of crafting the perfect instructions. Zero-shot versus few-shot learning. A zero-shot prompt asks the model to perform a task it hasn't been explicitly trained on, relying only on its pre-existing knowledge. A few-shot prompt includes a handful of examples to guide the model, which significantly improves performance. Chain of thought, COT, prompting. This revolutionary technique encourages the model to think step by step, breaking down a complex problem into a series of intermediate reasoning steps. This mimics human cognition and dramatically improves results on tasks requiring logic and reasoning. Advanced COT methods. Building on this, researchers have developed even more sophisticated methods like Tree of Thoughts, TOT, which explores multiple reasoning paths like branches on a tree, and Graph of Thoughts, GOT, which models reasoning as an interconnected graph, allowing for even more complex problem solving. 2. External knowledge retrieval. LLM's internal knowledge is static and can be outdated. This is where retrieving external information comes in. Retrieval augmented generation. This is the fundamental technique for combining an LLM's parametric knowledge, what it learned during training, with non-parametric information retrieved from external sources like databases or the internet. This gives the model access to current, domain-specific information. Knowledge graph integration. For structured information, knowledge graphs are incredibly powerful. Frameworks like Capping can retrieve relevant facts from a knowledge graph and add them to the prompt, grounding the LLM's response in verifiable data. 3. Dynamic context assembly. This is the final step where all the retrieved components, instructions, external knowledge, user query, etc., are orchestrated and formatted into a single, coherent context to be fed to the LLM. This process must be adaptive and optimized for the specific task and the model's architectural biases. 4.2. Context processing. Once the raw information is gathered, it needs to be processed and optimized. 1. Long context processing. One of the biggest technical challenges for LLMs is handling very long sequences of text due to the quadratic complexity of the self-attention mechanism. Architectural innovations. New architectures like state space models, SSMs, Mamba, and techniques like dilated attention are being developed to handle ultra-long sequences more efficiently, with some claiming to process up to 1 billion tokens. Optimization techniques. Methods like flash attention and ring attention cleverly use the GPU's memory hierarchy and distribute computation across multiple devices to make processing long contexts much faster and more memory efficient. 2. Contextual self-refinement and adaptation. This involves giving LLMs the ability to improve their own outputs. Self-refine framework. This is a powerful idea where an LLM is used to critique and refine its own output in an iterative loop. The model acts as the generator, the feedback provider, and the refiner, which has been shown to improve performance by up to 20% on some tasks. Reflection. This framework gives an agent a form of episodic memory, allowing it to reflect on past actions and linguistic feedback to make better decisions in the future. Autonomous evolution. More advanced systems aim to teach LLMs meta skills, allowing them to continuously self-evolve by generating their own training data or even discovering and implementing their own improvement algorithms. 3. Multimodal and structured context. The real world isn't just text. Context processing also deals with integrating other data types. Multimodal large language models, MLLMs. These models are designed to understand and process information from different modalities, such as images, audio, and video, in addition to text. A common technique is to use an external encoder, like CLIP for vision, to convert multimodal inputs into tokens that the LLM can understand. Structured and relational context. LLMs traditionally struggle with structured data like tables, databases, and knowledge graphs because they are designed for sequential text. Techniques like verbalization, converting structured data into natural language sentences, or using graph neural networks, GNNs, help bridge this gap, allowing LLMs to reason over complex, structured information more effectively. 4.3. Context management. This final pillar addresses the practical challenge of efficiently organizing and utilizing all this contextual information within the LLM's finite limits. 1. Fundamental constraints. Finite context windows. Every LLM has a limit to how much context it can handle at once. This is a major bottleneck for tasks that require understanding long documents or conversations. The lost in the middle problem. Research shows that LLMs are best at recalling information from the very beginning or very end of a long context, while information in the middle is often ignored or forgotten. Statelessness. By their nature, LLMs process each interaction independently. They don't have a native mechanism to maintain state or memory across conversations, which requires explicit management systems. 2. Memory hierarchies and storage architectures. To overcome these limits, researchers are building sophisticated memory systems for LLMs. OS-inspired memory. Systems like MemGP are inspired by how operating systems manage memory. They use a small, fast main context, like RAM, and a larger external storage, like a hard drive, and the model learns to page information back and forth between them as needed. Cognitively inspired memory. Other systems are inspired by human psychology. Memory Bank, for instance, uses the Ebbinghaus forgetting curve to dynamically decide which memories are important to keep and which can be forgotten over time. 3. Context compression. This involves techniques to reduce the size of the context while preserving the most critical information. Autoencoder-based compression. The in-context autoencoder, ICAE, can compress a long context into a much smaller set of memory slots that the LLM can then use, achieving up to 4x compression. KV cache management. A significant portion of an LLM's memory usage during inference comes from its key value, KV. Techniques like Streaming LLM and the heavy hitter Oracle, H2O, implement smart eviction policies to keep the cache size manageable, allowing the model to process infinitely long sequences with bounded memory. Chapter 5. System Implementations. This chapter moves from the building blocks to the finished structures. It explores how the foundational components of context engineering are integrated to create sophisticated, practical AI systems. 5.1. Retrieval Augmented Generation. RAG is a cornerstone of modern context engineering. It addresses a fundamental flaw in LLMs. Their knowledge is frozen at the time of training. RAG systems connect LLMs to external, dynamic knowledge sources, ensuring their answers are up-to-date and factually grounded. Modular RAG architectures. Early RAG systems were simple, linear pipelines. Retrieve, then generate. The new trend is toward modular RAG, where the system is built from reconfigurable components. This allows for more complex and flexible workflows, such as rewriting a query before retrieving, using multiple queries at once, or routing a query to the best possible data source. Frameworks like FlashRAG and ComposeRAG provide toolkits for building these sophisticated, customizable RAG pipelines. Agentic RAG systems. This approach elevates RAG by embedding an autonomous AI agent into the process. Instead of just passively retrieving information, the agent acts as an intelligent investigator. It can use reasoning and planning to decide when to retrieve information, what to search for, and how to use the results. These systems often have reflection mechanisms, allowing them to learn from past interactions and refine their retrieval strategies over time. For example, SelfRAG trains a model to generate special tokens that control when and how retrieval happens, making the process adaptive.
Graph-enhanced RAG. While standard RAG often retrieves unstructured chunks of text, graph-enhanced RAG leverages the power of structured knowledge, typically in the form of knowledge graphs. This has several advantages. It allows for multi-hop reasoning, where the system can navigate through the relationships in the graph to find answers to complex questions. It reduces context drift and hallucinations by grounding the LLM in the logical structure of the graph. Systems like HippoRAG and LightRAG use graph structures to achieve more precise and efficient retrieval, especially for questions that require connecting multiple pieces of information. 5.2. Memory systems. Memory is what separates a simple chatbot from an intelligent assistant. It allows an AI to maintain context over long conversations, learn from past interactions, and build a persistent understanding of the user and the world. Memory architectures. LLM memory systems are often designed to mimic human cognitive systems. Short-term memory. This is the LLM's working memory and is typically handled by its context window. Information here is immediately accessible, but is lost once the session ends.
Long-term memory. To overcome the limitations of the context window, long-term memory systems use external storage, like a vector database, to save information persistently. This allows the agent to recall relevant memories from past conversations or experiences. Classification. Memory can also be classified as parametric, knowledge baked into the model's weights, ephemeral, runtime states, or plain text, information retrieved via RAG. Memory-enhanced agents. Integrating these memory architectures turns LLMs into agents that can learn and adapt. Frameworks like Memos and Self-Controlled Memory, SCM, provide structured ways for agents to manage their memory, deciding what to store, when to retrieve it, and how to update it. The Rememberer framework allows an agent to learn from past successes and failures through verbal reinforcement, using self-reflection to improve its future actions. These agents are being used in a wide range of applications, from personalized recommendation systems, RecMind, to social simulations with generative agents that exhibit believable, persistent behaviors. Evaluation and challenges. Evaluating memory is incredibly difficult. There's a lack of standardized benchmarks specifically designed to test long-term memory. Frameworks like LongMemEval and MathDALBench are emerging to fill this gap, testing capabilities like temporal reasoning, knowledge updates, and multi-session consistency. A major challenge is that most LLM agents are still fundamentally stateless. They don't truly learn incrementally over time. This makes it hard to assess genuine lifelong learning. Another issue is isolating memory performance from other cognitive abilities. It's often hard to tell if a failure is due to a bad memory mechanism or a limitation in the agent's reasoning ability. 5.3. Tool-integrated reasoning. This implementation transforms LLMs from passive text generators into active world interactors. By giving them the ability to use tools, we allow them to overcome their inherent limitations, such as outdated knowledge or the inability to perform precise calculations. Function calling mechanisms. This is the core technology that enables tool use. The LLM is trained to generate structured output like a JSON object that can be used to call an external function or API. This process involves several steps. 1. Intent recognition. The model understands that the user's request requires a tool. 2. Function selection. It chooses the correct tool from a list of available options. 3. Parameter mapping. It extracts the necessary arguments for the function from the user's query. 4. Execution and response. The external tool is executed, and its output is fed back into the model to generate a final response. This evolution started with systems like Toolformer and has been standardized by OpenAI's Function Calling API. Tool-integrated reasoning. This is a paradigm where reasoning and tool use are deeply intertwined. Instead of just answering a question, the agent decomposes a complex problem into subtasks, where each subtask can be solved by a specialized tool. Frameworks like React pioneered this by interleaving thought, action, observation steps.
The model reasons about what to do next, thought, executes a tool, action, and then incorporates the result, observation, to inform its next step. More advanced systems like Chameleon can synthesize entire programs that combine vision models, search engines, and Python functions to answer complex multimodal questions. Agent-environment interaction. This is where tool use becomes truly interactive. Reinforcement learning, RL, is proving to be a powerful way to teach agents how to use tools. Instead of just being told how to use a tool, the agent learns through trial and error, receiving rewards for successful outcomes. This allows it to discover optimal tool use strategies on its own. Systems like Retool have shown this to be highly effective for tasks like mathematical reasoning. Search-augmented reasoning systems like Search R1 train models to make dynamic decisions about when to search the web and what queries to use during a multi-step reasoning process. Evaluation is a huge challenge. Benchmarks like MCP Radar and GTA are being developed to test tool-integrated systems on realistic, real-world tasks. Results show that even the most advanced models, like GPT-4, still struggle with complex tool use scenarios where humans excel. 5.4. Multi-agent systems. This is the frontier of context engineering, where multiple autonomous agents collaborate to solve problems that are too complex for any single agent to handle alone. This requires sophisticated mechanisms for communication, coordination, and orchestration. Communication protocols. For agents to work together, they need a common language. Early standards like KQML and FIPA-ACL laid the groundwork for agent communication based on Speech Act theory. A new ecosystem of modern protocols is emerging to standardize how LLM-based agents interact. These include MCP, Model Context Protocol, which acts like a USB-C for AI to standardize agent-tool interactions, A2A, Agent-to-Agent Protocol for peer-to-peer communication, and ACP for general-purpose messaging. This standardization is crucial for creating interoperable and scalable agent systems. Orchestration mechanisms. Orchestration is the brain of a multi-agent system. It's the infrastructure that manages how agents are selected, how context is distributed among them, and how the overall workflow is controlled. An orchestrator might decide which agent is best suited for a particular subtask based on its capabilities. It manages the flow of information, ensuring that agents have the context they need to perform their roles. Frameworks like AutoGen and Crew AI provide tools for building these complex, orchestrated systems where agents can take on different roles, e.g., planner, coder, critic, and work together in a structured way. Coordination strategies. Getting agents to coordinate effectively is a major challenge. Transactional integrity. In complex workflows, what happens if one agent fails midway through its task? The whole system can be left in an inconsistent state. Current frameworks often lack robust mechanisms for handling these partial failures. The Saga LM framework is one attempt to solve this by introducing transaction guarantees and independent validation. Context handling. Agents in a multi-agent system struggle with long-term context maintenance. Ensuring that all agents have a consistent and up-to-date view of the shared context is a difficult problem. Applications. Despite the challenges, these systems are already being used in diverse fields. In healthcare, they can perform complex medical queries by assigning subtasks to specialized agents. In business process management, they can simulate complex organizational workflows. Chapter 6. Evaluation. Evaluating context-engineered systems is a complex and evolving challenge. Because these systems are made of many interacting parts, retrievers, memory, reasoning chains, etc., traditional metrics used for simple text generation are no longer sufficient. We need a comprehensive approach that can assess everything from the performance of individual components to the emergent behavior of the entire system. 6.1. Evaluation frameworks and methodologies. 1. Component-level assessment, intrinsic evaluation. This focuses on testing each building block of the system in isolation. Prompt engineering. How effective is a prompt? This is measured by looking at the semantic similarity and quality of the response, as well as its robustness to small changes in the input. Long context processing. To test this, researchers use the needle in a haystack paradigm, where they hide a specific piece of information, the needle, in a very long block of text, the haystack, and see if the model can find it. This helps measure information retention and identify positional biases. Self-refinement. These mechanisms are evaluated by measuring performance improvement across multiple iterations. Frameworks like Self-Refine and Reflection have shown that models like GPT-4 can achieve up to a 20% performance boost through this process. Structured data integration. This is tested by evaluating the model's accuracy on tasks like knowledge graph traversal or generating SQL queries from natural language. 2. System-level integration assessment, extrinsic evaluation. This looks at the end-to-end performance of the entire system on a real-world task. The goal here is to capture emergent behaviors, both the good, synergies where the whole is greater than the sum of its parts, and the bad, interference where components clash and degrade performance. RAG systems. Evaluation covers both the quality of the retrieved information, precision, recall, and the factual accuracy of the final generated text. Memory systems. This is notoriously difficult because current LLMs are largely stateless. Benchmarks like LongMemEval are designed to test memory persistence over long interactions, and they've shown that even commercial AI assistants suffer a 30% drop in accuracy over time. Tool-integrated reasoning. Evaluation must cover the entire tool use process. Was the right tool selected? Were the parameters correct? Did the system handle errors gracefully? Frameworks like MCP Radar provide standardized metrics for this. Multi-agent systems. Here, evaluation focuses on communication effectiveness, coordination efficiency, and the quality of the collective outcome. It's crucial to test for transactional integrity to ensure the system can handle partial failures without leaving things in an inconsistent state. 6.2. Benchmark datasets and evaluation paradigms. For RAG, benchmarks are being developed to test advanced modular and agentic RAG systems, including their ability to perform multi-hop reasoning over knowledge graphs. For tool use, a host of new benchmarks have emerged. The Berkeley Function Calling Leaderboard, BFCL, provides 2,000 test cases to measure call accuracy and pass rates. ToolHop specifically tests multi-hop tool usage. Web Arena and Mind2Web evaluate web agents on thousands of real-world tasks across hundreds of websites, revealing significant performance gaps compared to humans. For general reasoning, the Gaia benchmark tests general AI assistants and shows that while humans achieve 92% accuracy, even the best models like GPT-4 only reach 15%, highlighting how far we still have to go. 6.3. Evaluation challenges and emerging paradigms. Current evaluation methods have significant limitations. 1. Methodological limitations. Traditional metrics like BLEU and ROUGE are inadequate for measuring complex, multi-step reasoning. Attribution is a major problem. When a complex, multi-component system fails, it's incredibly difficult to pinpoint which specific component was the root cause. 2. Emerging paradigms. New ways of evaluating are being developed to address these issues. Self-refinement evaluation. Instead of a single-shot assessment, this paradigm evaluates a system's ability to improve itself over multiple cycles of feedback and revision. Multi-aspect feedback. This moves beyond a simple correct-incorrect score to provide more nuanced feedback on dimensions like clarity, relevance, and robustness. Orchestration evaluation. For multi-agent systems, frameworks like Saga LLM are being developed to explicitly test for transactional integrity and robust coordination. 3. Safety and robustness assessment. This is a critical and often overlooked aspect of evaluation. We need to test how systems perform under adversarial conditions and distribution shifts. For agentic systems that can operate autonomously, safety evaluation is paramount. We need to assess their resilience to unknown unknowns, unpredictable failure modes that can cascade through a complex system. Alignment evaluation is also crucial to ensure that these systems adhere to human values and intended behaviors as they adapt and evolve over time. Ultimately, the field needs to move away from static benchmarks and toward dynamic, holistic assessments that can co-evolve with AI capabilities to ensure these powerful systems are also reliable, efficient, and aligned with human values.
Chapter 7: Future Directions and Open Challenges. Context engineering is at a turning point. While great progress has been made, the path forward is filled with both exciting opportunities and fundamental challenges that will require sustained interdisciplinary research. 7.1 Foundational Research Challenges. Theoretical Foundations. Right now, context engineering is more of a collection of techniques than a field with a unified theory. We lack the mathematical frameworks to understand the fundamental limits of these systems, predict how different components will interact, or provide principled guidelines for designing optimal architectures. Developing an information-theoretic analysis of context would help us answer questions like: what is the most efficient way to compose a context? How much information is redundant? Scaling laws and computational efficiency. The comprehension generation gap. This is one of the most critical challenges. LLMs are amazing at understanding long, complex inputs, but they are still very limited in their ability to generate equally long, coherent, and factually consistent outputs. We need to figure out if this is an architectural limitation or something more fundamental. Context scaling. The quadratic, O of n squared, cost of attention mechanisms is a major bottleneck for scaling to ultra-long contexts. While new architectures like state space models, e.g. Mamba, show promise with linear scaling, they are not yet as performant as transformers across all tasks. Multimodal integration. Integrating different data types, text, images, audio, video, graphs, is a huge challenge. Current systems often use separate encoders for each modality with limited interaction between them, failing to capture the rich interplay of information in the real world. Reasoning over abstract structures like graphs is particularly difficult, as their meaning is not easily captured by sequential models. 7.2 Technical Innovation Opportunities. Next-generation architectures. We need to look beyond the standard transformer. Memory-augmented architectures. We must move beyond simple external vector stores to create more sophisticated hierarchical memory systems. Developing a true episodic memory that can maintain a coherent long-term narrative is a key architectural challenge. Modular and composable systems. The future is likely modular. Architectures like Modular RAG allow for flexible systems that can be easily adapted and optimized by swapping out different components. Advanced reasoning and planning. Current LLMs are still limited in their reasoning capabilities. We need to enhance their ability to perform causal, counterfactual, and analogical reasoning. Multi-step planning. Systems need to get better at decomposing complex tasks, monitoring their progress, and adapting their plans on the fly. As benchmarks like Gaia show, there is a massive gap between AI and human performance in this area. Intelligent context assembly and optimization. Instead of relying on handcrafted heuristics, we need systems that can automatically optimize their own context. This could involve using reinforcement learning or evolutionary algorithms, prompt breeder, to discover the most effective combination of informational components for any given task. Self-refinement mechanisms also play a key role here. 7.3 Application-driven research directions. Domain specialization.
Real-world applications in fields like healthcare, law, and scientific research have unique requirements. We need better techniques for adapting general-purpose models to these specialized domains while ensuring safety, accuracy, and regulatory compliance. Large-scale multi-agent coordination. Scaling multi-agent systems to hundreds or thousands of agents presents enormous challenges in distributed coordination, communication, and fault tolerance. Standardizing communication protocols is a critical first step. Human-AI collaboration. We need to design systems that can work effectively as part of hybrid human-AI teams. This involves research into optimal task allocation, shared mental models, and trust calibration, ensuring that humans rely on AI systems appropriately without losing their own agency. 7.4. Deployment and societal impact. Scalability and production deployment. Beyond the theoretical challenges, there are practical issues of making these systems reliable, maintainable, and cost-efficient enough for production environments. Safety, security, and robustness. As these systems become more autonomous, ensuring their safety is paramount. We need comprehensive evaluation frameworks to test for potential failure modes, security vulnerabilities like prompt injection, and unintended behaviors. Ethical considerations. Finally, we must address the ethical dimensions of this technology. This includes mitigating bias in training data and model architectures, protecting user privacy, especially in systems with long-term memory, and ensuring transparency and accountability. Chapter 8. Conclusion. This survey has formally introduced context engineering as a crucial discipline for building the next generation of artificial intelligence. It moves beyond simple prompt design to the systematic optimization of the entire informational payload that large language models, LLMs, use to understand, reason, and act. By analyzing a vast body of research, a unified taxonomic framework has been presented, organizing the field into foundational components, how context is retrieved, processed, and managed, and system implementations, how these components are integrated into advanced systems like RAG, memory-enabled agents, and multi-agent collectives. Several key insights have emerged from this analysis. 1. A critical research challenge is the comprehension generation gap. While LLMs have become remarkably proficient at understanding long and complex contexts, they still lag significantly in their ability to generate outputs of similar sophistication and length. Addressing this asymmetry is a top priority. 2. There is a clear trend toward modularity and compositionality. The future of AI systems lies in flexible architectures where specialized components can be combined and reconfigured like building blocks to tackle diverse and complex tasks. 3. The integration of different context engineering techniques is creating synergistic effects, where the capabilities of the combined system are far greater than the sum of its individual parts. 4. Evaluation remains a major hurdle. Traditional metrics are insufficient for these complex, dynamic, and adaptive systems. The field urgently needs new, comprehensive evaluation frameworks that can assess not just task success, but also the robustness, safety, and alignment of these systems over extended periods. Looking ahead, context engineering will be central to AI development. The core idea that an AI's performance is fundamentally determined by the quality of its context will only become more important as we build more complex, autonomous, and integrated systems. This survey provides a roadmap for this future, establishing a clear set of principles, methodologies, and challenges to guide innovation and ensure the responsible development of truly context-aware AI. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.